All right, we'll finish the last couple of things that are left for the case study 1 module. So we talked about CT last time. The last application I want to talk about for matrices are graphs. Okay. A graph is simply a set of nodes connected by edges. Okay. And usually you'd see somebody draw nodes like this. And each node might represent something of interest, okay, to you. And graph theory is widely applicable. So this is a very useful idea that can be used for representing lots of different things. Okay. For example, these could be locations of places geographically, and the lines that connect these two could tell you if there is a direct, let's say, a road connection between them, right? Or, for example, these could be ideas in some subject, and the lines could indicate whether or not those ideas are connected, right? So it's very general, right? And a graph, if you were to define it formally, it's simply a set of nodes. Say this is node 1, I'll call it node 1, node 2, node 3, node 4, node 5. Set of nodes and a set of edges. Let's say I'll call it 1, E2, 3, 4, 5. So you simply have a set of nodes or vertices. These are also called vertices. And edges. V represents the set of nodes. E represents the set of edges between the nodes. Okay. So in this particular case, your V would simply be N1, N2, N5. And there are 5 edges here. So your edges would simply mean E1, E2, E5. Okay. And it turns out that this connectivity pattern that you have in a graph can be represented using a matrix. Okay. And before that, there are other possibilities as well. So, for example, you could have a graph like this, where the edges actually have no directional properties. It just says they're connected. It does not mean, and something like this is called an undirected graph. You could have directed graphs as well. Okay. For example, if you take the geographical example, geographical locations example, uh, you might have arrows like this, which means the connectivity is in only one direction. That means if you're at N1, you can go from N1 to N2 and there is nothing for you to travel back, right? So you could, or if you have arrows like this where the edges actually have directions, then it's called a directed graph. In both cases, you can use matrices to actually represent this connectivity pattern. There are multiple ways to do this. One approach is the approach of using adjacency matrices, or what are called adjacency matrices. See, matrix. It simply tells you if two nodes are adjacent to each other, which basically means are they connected by an edge. Okay. Undirected or directed. For now, we'll only focus on undirected edges. We'll not worry about directed edges. Okay. And an adjacency matrix is a n cross n matrix, where n is the number of nodes. Okay. So the rows correspond to your vertices. If you're talking about undirected graphs, right, we will never have something like this, a connection back to a node itself. Okay. And an element here in the adjacency matrix, Aij, simply tells you, for now, let's say we are simply interested in whether or not there is a connection between node I and node J. Aij is equal to 1, 1 if there is a connection between I and j, 0 otherwise. Okay, that's the definition for the adjacency matrix. And so if that is the definition, if that's how we want to build the adjacency matrix, what can you say about the diagonal and what will be the size of this matrix for this particular example? Well, it's a 5 by 5. 5, 5. What can you say about the diagonal elements? Yeah, they will all be 0 because there are no loops here. Okay. If you have directed graphs, you might have situations where there is a loop. Okay, but undirected graphs, you don't have that. So these will all be zeros. 2, 3, 4, 5. What can you say about the A1, 2? Well, we are dealing with undirected graphs. What is A1, 2? That simply means is there a connection between node 1 and node 2? There is, right? So that's 1. This next one, you can tell me from by looking at this. 0, is it? Connection between 1? Yes, there is no connection between 1 and 3. 1 and 4? No. 1 and 5? No. Hey, and what we are representing here is direct connection. You could argue that there is a connection between 1 and 5 because you can go like this or like this. That's not adjacency. Adjacency is, are they right next to each other? That means is there a direct link between them with no nodes in between. What about this? 1 or 0? 1. Because all we've said is there a connection? That's all. 1. What about 2, 3? 2, 4? 2, 5? Okay. We know these two. What will be this? 3, 1, 0. Yeah. 1. 4, 5? 4, sorry, 3, 4. 3, 3, 4 is 0. Yeah. Okay. Is 1? Yeah. 3, 5 is. Yeah. Just say it out. It's fine. What are the elements here? 0, 1. Is that right? Okay. And the last one? Okay. For an undirected graph, the adjacency matrix is a square matrix. The diagonal elements is 0. What else do you see? What other property does this matrix have? Square matrix. Is the matrix symmetric? What is the definition of a symmetric matrix? Did we talk about that? Did I define symmetric matrices? No. Okay. So symmetric matrices. Okay. Symmetry. Tree. Right? This is the property that applies for square matrices. You say a matrix is symmetric if A transpose equals A. Right? That means the elements about the main diagonal are mirror images of each other. Okay. In this case, the adjacency matrix A is a symmetric matrix. Okay. You can use the concept of the adjacency matrix even for directed graphs. Okay. Okay. But in this case, the definition would be slightly different. For directed graphs, Aij would be 1 if there is an edge starting at I and ending at j. Otherwise, it's 0. Okay. If that is the case, what would be A here? 5 by 5, it'll still be 5 by 5. Diagonal elements are all 0. Okay. Now you have to be careful. It's not just any line. If we're saying 1, 2, the edge starts from 1, ends at 2. It looks like there is 1 there, so that's okay. And then zeros. There's nothing. What about here? A2, 1. It'll be 0 because there is no arrow going back. A2, 3. Is it 1? Yeah, okay. And then A2, 4. 1, 0. 1 is it? 3 to 5. Okay. 4, 0. And 5. All zeros, is it? Okay. This would be for a directed graph. There are other conventions as well. People might use a sign, for example, signed numbers for these. But this is one way to represent a directed graph. Okay. In this case, of course, it's not symmetric anymore because the a line is symmetric and arrow is not. Right. See, I think if I remember correctly, depending on the direction of the line, you can say +1 or -1 or something like that. Yeah. Okay. Right. So this is one useful application where you can use matrices for representing matrices, and it turns out it's not just to represent stuff. In fact, once you have the matrix, you can use it for asking interesting questions. I mean, this will be there in one of your assignments. If you have a matrix A that's an adjacency matrix, A square tells you something about the number of the paths that you can take from one point to another. For example, if you look at the adjacency matrix A, right, any one element tells you if there is a direct link between those two nodes. A square tells you if there are paths between I and J that involve one node in the middle. That means it's two paths, and will tell you the number of such paths. If you take A cube, it tells you how many paths do you have with two intermediate stops in the middle, and interesting stuff like that. So this not just once you see this matrix, it not just tells you how to draw this graph, but uh, there are other things that you can derive from the matrix which are actually quite useful. Okay. So we will use this idea of graphs in our next or case study 1B, which is essentially going back to our data, the reports.csv file. And this time, we are not interested in clustering our data. So we have our nodes, the medical nodes, and then we have a set of keywords. Let's assume we have no idea about what these keywords mean. All we are interested in is knowing which of the keywords that we have are related to each other. Okay, in some sense, it could be in any way. But what we are specifically asking is, or we are defining relationship between two keywords as them occurring together in a report. For example, if you have a medical report from a specialty, right? If token 1 and token 2 often appear together in these reports, then it's possible that two of them are somehow related, right? Medically, right? There are different ways to define this. For us, we are simply saying if you have two tokens and they appear together in a segment of text. For us, it's that entire report. You could say if it appears together in a sentence, they're related, and things like that, right? That's up to you. In this particular example, at least, I've defined it as we have a bunch of reports. If two tokens appear together in a report, then we say they're somehow related. If they repeatedly appear together in reports, then we say that they are connected to each other. And what we want to do is we have these tokens and we want to build a network like this, not a directed one, undirected one. Let's say we have 5 tokens. We want to build a network like this to know which of these tokens or concepts are related to each other. That means they occur together. That means there must be some common meaning to them, or they must be related to something. Right? So that's what we're doing. So again, you should be able to run this notebook. So what we do here, same thing, you get the data. Right. Right. So the first thing we do to build this matrix, right? To build this, so we want to build this graph, and the way we want to do that is to first start by building this matrix. Okay? We'll see how we do that. Okay? So we have a bunch of reports, right? So we have reports, right? 1, 2, 3, so on and so forth. And we have a bunch of tokens. So we'll first start by building a table or another matrix where the rows correspond to your reports. Okay. And the columns correspond to your tokens, T1, T2, so on and so forth. Let's say M. Okay. And the number of reports it says N. Okay. So you take the first report and then you find out which of these tokens are present in that report. Okay. If it's present, you give it a 1. If it's not present, you give it a 0. Okay. So we build 1, and so on and so forth. So you build this matrix, right? Now, if you want to know if two tokens are related to each other, right? Let's say we are interested in whether token 1 is related to token 2. If you take these two columns, right? If they are related to each other, more often than not, if there is a 1 here, there should be a 1 here, right? That means the two of them occur together in a report, right? So if you see that more often the ones occur together in these two columns, then you'd say, well, then they are probably related. But if you have situation like this, where if it's 1, this is 0. If you see situations like this, that you see in each report this occurs, this does not occur. In this report, T1 does not occur, T2 occurs and stuff. Then you say, no, they're probably not related because they don't appear in the same report, right? So it looks like if you generate this matrix, right, by simply looking at you can derive or you can come up with an estimate for the relationship between T1 and T2. The exact relationship you're looking for is co-occurrence. Do they occur together in reports? By simply looking at corresponding elements, right? One way to quantify that is if you think of this as a vector, right? Think of this as another vector. Let's say I want to count the number of times the two tokens occur together. How might I do? How would I do that? Let's do an example, right? Let's say we have 5 reports and we're looking at 2 tokens. I have these 2 columns, token 1, token 2. I want to count the number of times the 2 tokens appear together. How would I do that? And one thing is you simply count the number of rows. The 2 of them have ones, right? Or another way to do that is you take the 2 of them, you multiply them, and then you sum them, right? Because it'll be 1 only if they're both ones. Otherwise, it'll be 0. But we know an expression for that operation, or we've defined that operation before. If we take 2 vectors, multiply their individual elements, and add all of them together, what is that operation? Yeah, the standard inner product. If this was x and this was y, you simply take transpose y. And this now tells you, in this particular application, this tells you the number of times the 2 tokens occur together. Okay, so and you get a scalar here, and this is great because now the number that I get simply tells me if 2 tokens appear together. The larger the number, the more likely that the 2 concepts are related. Okay, if it's 0, then it means they never co-occur, at least in the data set that we have. Okay, so that's one way to quantify co-occurrence. But when would you say that this number that you get for X transpose Y is actually large enough for you to say they occur together? If it's 0, of course, you say no, they're not, they don't occur together. But if it's 3, is that a large enough number? In this case, you get 2. Is that big enough? Or let's put it this way. Say it was like this, and you get 3. On the other hand, the number of here we've only considered 5 reports, whereas in the data that we have 1,500 reports, right? And there, let's say there you get the inner product to be 3. Is that a big number or a small number? There you would say no, it's not big enough, right? So it means just the X transpose Y is not enough. You have to somehow normalize it, because by simply having more elements in X and Y, a longer vector, this number is, even by random, right, can come out to be a large number. Right? If you had a million vector that had a million elements, it's possible that your number might come out to be 1,000, and it might not be a big number. I mean, it's definitely not a big number compared to million. Right? So we would have to normalize it. Right? And one way to do that is you simply take X transpose Y, and you simply divide it by the size of X and Y. Okay, provided the two of them are not 0. If any one of them is 0, then of course you cannot do this. Right? You do this, and let's say we call this or C. I think I call it C. A measure of co-occurrence. This is when X, both of them are not equal to 0. Okay. If one of them is 0, then we'll simply define it as, we'll say C cap is 0. This is, we are defining it. If any one of the columns is 0, right, then we define the co-occurrence to be 0, because the denominator is 0. Okay. Okay. If any one of the columns is 0, right, what does that tell me about the token? It does not appear in any of the reports. So it makes no sense to ask, do things co-occur, right? That's why we put in this extra condition and say, there is this measure of co-occurrence, we define it as 0 because that word never appeared. So it makes no sense to ask, does it co-occur with any other word? But if the two tokens that you're looking at, or two words that you're looking at, do co-occur, or sorry, it do occur in your reports, then it makes sense to ask, what is the measure of co-occurrence? Okay. And we've also seen this before. This is not an arbitrary quantity, right? We've seen this in the first lecture. What is this? Sorry? Yeah. Not this angle. What of angle? Yes. This is cos. But what is that angle? What is theta? Angle between what? Which two vectors here? Yeah, it's X and Y. So you can now think of this idea of co-occurrence. You can simply think of it as essentially the angle between the vectors representing the occurrence of these tokens in your reports. So what you're essentially quantifying there is the cos of the angle between these two. Okay. Right. So what we will do then now, from now on, we'll simply use this as a measure of co-occurrence. Yeah.
There's only one such course.
One such. Okay.
Okay, that one.
Okay. And everything else is 0.
Then I'll capture.
Yes. Agreed. See, there are issues with this. Right. For example, like Divakar pointed out, if X and Y occur only once, right, in one report, there is a problem with this measure, right? Because this will tell you they perfectly co-occur. Okay. In that case, this cos theta might not be a good measure. And in fact, no matter what measure you come up with, you will always find cases where it does not do that well, right? But this idea of doing x transpose y and then normalizing it by the length of the vectors is a simple enough approach for the first pass, right? Later on, you might say, okay, well, you might then weight it depending on the number of times x and y occur and things like that. You can do other things. Yeah, but for now, we'll simply use this as our first measure that we're going to use for building the graph. Okay. Okay. Now, this matrix, right? We'll call this O, occurrence matrix. That simply tells you whether or not a token appears in a particular report. And if you normalize this occurrence matrix, right, each of the columns, okay, by the length of that column, okay, if the length of the column is 0, you simply do nothing to that column, right? And let's say that matrix is O cap. O cap is simply the columns are all normalized to have length 1. If it's a 0 column, you leave it as it is. You leave it as a 0 column. Okay, so you derive O cap from O by normalizing. Okay, and we can now compute this co-occurrence matrix by simply doing this. If you do this, you will get this co-occurrence matrix, which is of size number of tokens times number of tokens. It's M. This will be M. Okay. And the C ijth element of this matrix will simply tell you O cap I transpose J. This is simply Cij is simply cos of the angle between the normalized vector representing the ith token and the normalized vector representing the jth token. Is it clear? And now once you have this C cap, you can use the C cap to build your graph. Okay. So let's say you draw your different tokens like this. Nodes, I've taken 5 tokens, right? CII is not interesting. CII will always be 1 because token 1 always occurs with itself, so that does not matter. We'll only bother about Cij, where I and j are not equal. If this number is close to 1, let's say, that means they often co-occur, then let's say this is I and j, then we draw a thick line between them. If they never occur, if this is 0, then of course, then you draw no line. If it's, let's say, a small number, 0.1, right, then you maybe draw a thin line between. Okay. If you do that for all possible ij's where I is not equal to j, then you get this graph that tells you how the different concepts are related. So if you do that, right, that's what I've written, done in this notebook. Yeah. So this is these are the columns, I think, no, rows from the occurrence matrix O. And then whatever I've said here, I've explained it here, so I will not go through that. Yeah. So if you build this co-occurrence graph, right, you get something like this. So we have a total of 50 tokens from token -010.txt file. The thick black lines tell you that the concepts are strongly related, relatively strongly related. They might not be equal to 1. There might be some value that is relatively high. The thinner, lighter lines, which are in the background, indicate that there is a weak link. That means they don't often co-occur. Yeah, so it looks like all these words, right? They all have connections between them. That means they all tend to co-occur in reports. And in fact, all of these also tend to co-occur with this word rating. I don't know what that is. Some word rating co-occurs with these, and another word tended also tends to also co-occurs with these. So you can look at the notebook, look at the connection pattern, and then see if it makes sense. A couple of observations you will make is some concepts that might be related actually do have a dark line between them. For example, sprain and tendonitis, there is a dark line. They are related. So sprain, you might have tendonitis in sprain when you have a sprain. But there are also other concepts that have a strong line, but make no sense. For example, relate and impress. Right? It seems very arbitrary. Okay, that there is a strong line between them, and that might not have anything to do with medicine. It might just be an artifact of the English language itself. Maybe relate and impress are often used by people when they write reports and things like that. Right. So the interpretation of this has to be done carefully. Right? I've listed some of these issues here. You can go through them. And then there are about 7 questions that you basically answer based on this, right? So this would be another application of the concepts that we've learned: inner product, norm, building a matrix, and then that matrix, the elements of that matrix having some meaning for the application that you're working with. Okay, all right. So that's all I wanted to say for the case study 1 module. If there are any questions about yesterday's material and today's material so far, we can discuss that now. Else we move to the next module.